Hello all, myself Shimmi Ashokan. I am an assistant professor in the Department of Computer Science and Engineering at Rajagiri School of Engineering and Technology. This presentation is to introduce the course Logic for Computer Science. Logic for Computer Science, it's a course which is included in the curriculum for BTech program in Computer Science and Engineering by Dr. APJ Abdul Kalam Technological University. And this particular course is offered as an elective during the 5th semester. So in this presentation, we will be discussing why actually as computer science students, you need to learn this particular course on Logic for Computer Science, and where exactly you can apply the concepts that you have learned from this course. And also we will discuss what constitutes this course, that is the contents of the course. And so I welcome you all to this presentation as well as all the subsequent presentations on this course Logic for Computer Science. So before we move on to the contents of the course, we will actually see why actually you need to learn this particular course. So we will begin with certain bugs that has occurred in the industry. Like say you might have heard about the Pentium FDIV bug. This bug, the Pentium FDIV bug, it's a computer bug which affected the floating point unit of the early Intel Pentium processor. And this bug was discovered in 1994, and the error actually occurred when dividing floating point numbers that occurs within a specific range. See, for example, suppose we have two floating point numbers. See here, the two floating point numbers. When these floating point numbers are divided, the correct answer is 1.33382044913624100. This is the correct answer. Whereas the Pentium processor, the result obtained by computation was like 1.3337390689002, etc., etc. So you can see what minute the error is. Even if the error was minute and occurred only at times, Intel had to recall all the defective processors, which came around 3 million to 5 million. And the bug ultimately had cost Intel a loss of $475 million. Now, another case is like Ariane 5 rocket explosion. This actually occurred in 1996. What happened is the rocket was launched by European Space Agency, and just after 40 seconds after its liftoff, the rocket exploded. The development cost of the rocket was $7 billion, and it actually took a decade for developing the rocket. And finally what resulted was like the rocket exploded just after 40 seconds after its liftoff. This again happened when during a conversion, like a 64-bit floating point number which was related to the horizontal velocity of the rocket was converted to a 16-bit signed integer. And what happened is when this number became larger than the maximum limit, that is 32,767, the conversion failed, and that failure resulted in exploding the rocket. Now another case, the third case. See here, between 1985 and 1987, Therac 25, it was actually a software controlled radiation therapy machine, and it administered overdoses of radiation, and at least 5 patients were killed between these years, 1985 and 1987. And similar event happened during 2000 also, when the software, which was written by an American company, it caused overdoses of radiation, and five persons were killed and 9 were affected seriously. So due to overexposure to radiation. So we have seen 3 different cases. In the first case, a minute bug in the software has resulted in a huge financial loss for Intel. In the second case, again a minute software bug has resulted in a mission failure as well as a financial loss. And in the third case, it's not only the financial loss here, it has resulted in loss of human life. So the problem is like when software controls critical structures, we need to ensure that the software is error free. We will see some other examples also. Before that, see, now we have the cyber physical systems. Cyber physical systems, these are actually systems where the computing and networking technologies are tightly integrated to the physical world. And the application of cyber physical system is in the area of medical devices, in the field of automotives, in the field of robotics, aeronautics, process control, etc. And when it comes to cyber physical systems, see, here we will see some examples, some software bugs that has happened recently, like the Arkan anesthesia machine. This again, there was a software defect in the machine, and the machine was manufactured by Space Labs Healthcare, and they had to recall the machines in 2014. And the problem was like when a cell phone or other USB device was plugged into one of the 4 USB ports for charging, it causes the system to stop working. So that was due to some minute software defect. Another case is where a software related bug, a software defect, prevented the airbags from deploying during a crash. In the case of GM Motors, the GM Motors had to recall 4.3 million vehicles due to this defect. And the same thing happened to Nissan also in 2014. Nissan had to recall a huge number of vehicles due to airbag malfunction. So in all these cases, we have seen that it's just a minute software error that has resulted in the financial loss for the company, for the manufacturers. Now, see, now we have self-driving cars. And see, this is a Tesla car. The Tesla car keeps on driving, and see, when a trailer takes a left turn just in front of Tesla, Tesla couldn't detect the trailer. Tesla ran into the trailer and it struck some fences and all. So when it comes to self-driving cars, safety is a critical concern. Now again, in 2018, a software bug has led to the death of a pedestrian while in Uber's self-driving car crash. What happened is like the car's sensor, it didn't detect the pedestrian, or what it happens is it detected, but it decided that it was a false positive. It considered that it had detected some empty say soda bottle in the road, and it kept on driving, and that ran into the pedestrian, and it has resulted in the death of the pedestrian. So all these cases were shown just to make you aware that even minute software defects will result in huge loss when the software controls critical structures. So we have seen that cyber physical systems. We will see why the verification of cyber physical systems is important with respect to automotive domain and medical devices domain. Say in the modern automotives, we have hundreds of ECUs which will be controlling all the critical functionalities of the vehicle, like anti-lock brake system, the powertrain, the cruise control, the airbag, the lane assistance, and also it is used for autonomous driving applications. And so what happens is improper functioning could lead to accidents and death. Again, when it comes to medical devices, we have a network of medical devices like pacemakers, nerve sensors, infusion pumps, which interacts with the human body. And now we have the surgery which is conducted by robots. And in all such cases, improper functioning may cause death. or may result in the loss of human life. So what happens is we need to verify such systems. Not only verify, we need to actually ensure that such systems are error free. The softwares are error free. And now when we consider the traditional methods of verification, the traditional methods are testing and simulation based analysis. And see, when you consider testing, during testing what we do is we select some test cases or certain scenarios and we will test those scenarios. Okay, so it will help us to detect the presence of bugs, but it will depend on the correctness will depend on how we select the test cases. We will be choosing only a particular set of test cases. We will not be doing an exhaustive testing. Exhaustive testing is not possible also. So using testing or simulation based analysis, we cannot guarantee correctness of the system. And now when it comes to the era of self-driving or autonomous cars, how actually can we decide how much testing is required to ensure the safety? We can't actually decide how much testing is required. So instead of going for traditional methods of testing, we will have to go for some other technique, and those techniques are called the formal methods. The formal methods for verification or formal methods for testing. Formal verification will help to deduce absence of errors. It will actually give us a guarantee that, see, your system is error free, you can use it. It will give us a guarantee. Okay, and what is formal verification? Formal verification is the mathematical based tools and techniques which are used for analysis and synthesis of hardware and software systems. And software verification was not actually used in industry because of the learning curve. The learning curve was too high. But now since we have the cyber physical systems and we have software controlling almost all the critical things, critical infrastructures, we need formal, all the certifications have included formal methods also into it. Like say DO 178C. This is actually a certification document. It is a primary document by which the certification authorities such as Federal Aviation Administration, Transport Canada, etc. approves all commercial software based aerospace systems. So this particular document has got a section recommending formal methods for analysis. So now it has come to a stage that only if you use formal methods for verification, you get a certification. So people in the industry are now forced to use formal methods. And now we will see what exactly is formal verification. Say formal verification, to verify the system, what we need to do is we need to model the system. We need to formally model the system. And to formally model the system, we will be using or we will be modeling it using some or as a state transition system. We may be using some kind of an automata or a state transition system to represent our system that is to be tested. Okay, so we model the system as a state transition system, and that will be one input to this verification system. Okay, this verification will be performed by some automated tools, like we may have model checkers or theorem provers, which are automated tools which performs verification. And to this verification system, one input will be the formal model of the system that is to be tested, and the other input will be the property that the system should satisfy. The property that the system should satisfy will again be written formally. We call it a formal specification. Formal specification. So the input to this verification system or the model checker or theorem prover will be a formal model of the system and the formal specification. See, I repeat, formal specification is the property that the system should satisfy, written or represented formally. Okay, for example, let us consider an operating system. We will have to represent the operating system as a state transition system, and the property that the operating system should satisfy. See, one property the operating system should satisfy is always operating system should not deadlock. Okay, so it should not result in a deadlock state. So always not deadlock or no deadlock is one property that operating system should satisfy. Okay, so what we do is we model the operating system, we give it as an input to the model checker, then we formally represent the property, say no deadlock or not deadlock. That will be represented formally, and that also will be given as input to the model checker. The model checker, what it does is it will exhaustively perform a verification on the system. It will check whether this particular property fails in some particular run of the system. If the property fails in some particular run of the system, it will generate a counter example. So the output the model checker gives will be, it will check whether the property is satisfied. If the property is satisfied, it will give you a guarantee that your system is error free. If the property is not satisfied, it will give a counter example. Counter example will be a run of the system in which the particular property fails. Okay, a particular run of the system in which that particular property had failed. Okay, now see, coming to this formal specification, to represent the properties formally or to write a formal specification, we need a logic. Okay, so this is where our course actually applies. The logic that we learn from this course, we apply it to write formal specification. Okay, which are actually the properties that your system should satisfy. Okay, and the logic that we use for representing formal specification or for writing formal specification is the temporal logic. Temporal logic we will be discussing in the 5th module. Okay, so most of the computing systems uses temporal logic for representing the properties. But we cannot directly go into temporal logic. We need to learn the basic things. That is, we need to learn propositional logic and predicate logic before we move on to temporal logic. Okay, so suppose, so I hope you got an idea on where your particular course or the concepts that you learn from this course applies. Okay, now the name of our course is Logic for Computer Science. So what is logic? What is logic exactly? Let us see an example. You all might have watched Tom and Jerry shows, right? So let us make some statements. The first statement is, no cat can catch Jerry. The second statement is, Tom is a cat. From these two statements, see, these two statements we call them as premises. So from these two statements, can we conclude that Tom cannot catch Jerry? So this is the conclusion. The last statement is the conclusion and the first two statements are the premises. Okay, the premises and the conclusion. Now another example is like, see, all rabbits have fur. Some pets are rabbits. Can we conclude that some pets have fur? And so in all these cases, this is actually how we actually use logic. Okay, and now another example. See here, penguins are black and white. Some old TV shows are black and white. Can we conclude that some penguins are old TV shows? So this is where the problem of representing logic using natural language occurs. See, logic, when it is expressed in informal natural language, it can be flawed. Okay, this statement is totally absurd, right? So we cannot make such a statement. So logic, when it is expressed in informal natural language, can be flawed. So we cannot use natural languages like English to represent logic. Instead, we will have to use some formal methods or some formal logic has to be used. Formal language has to be used. So we need to formalize the valid methods of reasoning. Okay, and the study of logic, it has begun with the ancient Greeks, and syllogisms were the most widely known set of rules. So these kind of statements are called syllogisms. And finally, a logical system, it will consist of axioms and rules of inference. And the properties a logical system should satisfy are consistency, independence, soundness, and completeness. Consistency, what it means is, a logical system is consistent if it is impossible to prove both a formula and its negation. See, you cannot prove P and negation P. You can either prove P or you can prove negation P, but not both. It is impossible to prove both the formula and its negation. Then we say that the logical system is consistent. Then independence means that, see, we have seen that the logical system consists of axioms. The axioms in a logical system should be independent. That is, no axiom can be proved from others. We will use axioms to prove formulas in the logical system, but we cannot prove one axiom from another axiom. Okay, so that is independence. Then the third property is soundness. Soundness states that all theorems that can be proved in the logical system are true. And completeness says that all true systems can be proved in the logical system. So these are the 4 properties a logical system should satisfy. So that is a basic idea on logic and why exactly you need to learn logic for computer science. Now coming to the different logical systems, the different logical systems that we will be learning are propositional logic, the first order logic or predicate logic, and the modal and temporal logic. Okay, so with that we will move on to the contents of this course, the syllabus of this course. We have 6 modules in this course. The first module, the first half of the first module, we will be just having a very brief discussion on the different topics that will be discussed in the rest of the modules. We will see what propositional logic is, what first order logic, what modal logic, and what temporal logic is. And we will have a brief introduction to program verification. From the second half onwards, we have a detailed discussion. Okay, so the second half of the first module, we discussed propositional logic in detail. We discussed the syntax and semantics of propositional logic. In the second module, we will discuss a deductive system called Hilbert deductive system for propositional logic. And we also will see resolution in propositional logic. In the third module, the first half we deal with binary decision diagrams, and the second half we start predicate logic. So the syntax and semantics of predicate logic will be discussed in the second half of the third module. In the fourth module, again we have a deduction system for predicate logic, and we will be discussing resolution in predicate logic. The fifth module is on temporal logic. We will be discussing the syntax and semantics of temporal logic, as well as we will discuss a deduction system of temporal logic. And in the fifth module, the first half of the sixth module, we will be discussing program verification. We will see what program verification is and how program verification can be done. And in the second half, we will have an introduction to modal logic. We will see the syntax and semantics of modal logic and an axiomatic specification, an axiomatic system of modal logic. Okay, so these are the contents of your course on your course Logic for Computer Science. Now coming to the textbooks, these are the textbooks and the references. Out of these, the second textbook, the one by Ben Ari, is the one that we will be using for discussing most of the modules. The first textbook, Arindama Singh, will be used for discussing the sixth module, that is the program verification topic as well as modal logic. In the sixth module, we will refer to this book. For the rest of the topics, we will be referring Ben Ari. Now coming to the objectives of this course. The objective of the course is to introduce the concept of mathematical logic and its importance, and to discuss the different logical systems, propositional, predicate, temporal and modal logical systems and their applications. And coming to the outcomes, once you complete the course, you should be able to explain the concept of logic, the importance of logic, and you also should have a clear understanding of the concepts in propositional logic, predicate logic and temporal logic, and you also will learn how to apply these resolution techniques in all these logical systems. And again, another objective is like you will have you should have a good understanding of the concept of program verification and how it can be applied in the real world scenarios. And finally, you should be able to explain the concepts in modal logic. So these are the course outcomes. And now a bit of motivation before we conclude this lecture. See, nowadays formal verification is used by almost all giant companies, giant manufacturers or giant MNCs companies. Almost all the companies, they use formal verification for verifying their systems, and a lot of research is going on in IBM, TCS, etc. on formal verification. So these are some of the companies in which formal verification is used for verifying their products. So that is all with an introduction to the course Logic for Computer Science. Thank you.